All right, welcome back. Let's do a little bit of grind 75. We're on the last question. Week 3, number 8. Evaluate reverse Polish notation. All right, so we got to learn Polish notation before we can go reverse. You are given an array of strings, tokens, that represents an arithmetic expression in a reverse Polish notation. Evaluate the expression, return an integer that represents the value of the expression. Okay, so don't return a string, return an int, even though we're getting a list of strings. Note that the valid operators are plus, minus, multiply, and divide. Each operand may be an integer or another expression. The division between two integers always truncates towards 0. Okay, so if it's positive, you want to round down. If it's negative, you actually want to round up. There will not be any division by 0. Okay, so we don't have to check for it. The input represents a valid arithmetic expression in a reverse Polish notation. Okay, so it's valid. We don't have to do error checking or some type of edge case checking. The answer and all the immediate calculations can be represented by a 32-bit integer. So for our computer, it will not overflow, and we don't have to do some type of subtracting the second factor thing so it doesn't overflow. What is reverse Polish notation? RPN, also known as reverse Lukasiewicz notation. It's probably wrong. Polish postfix notation, or simply postfix notation, is mathematical notation in which operators follow their operands, in contrast to prefix or Polish notation, which operators precede their operands. Okay, so it follows like this 3, 4. I'm just going to go ahead and take a note. 3, 4 plus instead of plus 3, 4, like you would see in closure or scheme. And these would be, let's say this is post, this is pre, and this would differ from what you're used to in class, which is an infix operator, where it's 3 plus 4. And you can imagine the infix operator makes more sense in math class, but if you had a function like add, and it took in a 3 and a 4, this is actually before, right? So this is closer to the pre, as an example. But, okay. So postfix describes general scheme, whereas the term reverse Polish refers to a specific method used to enter calculations into hardware or software calculators, which often have additional side effects and implications depending on the actual implementation involving a stack. Okay, so stack's a data structure we're familiar with, and here we're, getting familiar with this in terms of computation. There's probably calculators that use this that I've never used before, but the first computer to use postfix notation, there we go. There's a computer or calculator, though it long remained essentially unknown outside of Germany, was the Z3 in 1941. What is the Z3? Okay, so that's not a calculator. That is a room-sized computer, and this used postfix. All right, we don't have to go into this deep rabbit hole. We can look at computers and slide rules and a lot if we kept going, but let's just keep it to the actual RPN. Okay, so let's just look at the explanation. I think that's all we could, probably all we need to read. Don't really need to look at a ton of this, but there's a lot of history here, and it looks like even this has a, it's the programmer one. Okay, let's look at the explanation and we'll go back. So in reverse Polish notation, the operators follow their operands. For example, to add 3 and 4 together, the expression is 3, 4 plus rather than 3 plus 4. That's what we wrote right here. Cool. And the convention notation expression 3 minus 4 plus 5 becomes 3, 4 minus, okay, so 3, 4 minus means when you're given a 3 and a 4 and you subtract it, or you have a minus, then this becomes evaluated, right? So this becomes 3 minus 4, which equals -1. And then you have a 5 here and a plus. And then this becomes evaluated, the -1 plus the 5. And then you get a 4. Okay. And they're saying that this is, I guess, typically done in a stack. So if you imagine a stack of trays, a stack of numbers, then on the stack, this 3 is put first, the 4 is put first, and then the negative, right? And actually, probably by the time you get this negative, you can evaluate it, right? So this probably evaluates to that -1. So your stack has just a -1. You put the 5 on the stack, you put the plus on the stack, and you can go ahead and evaluate this, right? This becomes, I guess, a new version of a stack, and that becomes a 4, right? So you have you have 2 operators here, and the operands, I'm going to go ahead and make the operators red, so it's easy to see, and then the operands here are yellow, right? So it's almost like just a diagram is it's the code itself, right? We're probably going to keep a stack just like they've explained in the calculators. Okay, so the concept of stack, a last in first out construct, is integral to the left to right evaluation of the RPN. In the example 3, 4 minus, first the 3 is put onto the stack, then the 4 on top and the 3 below it. The subtraction operator removes the top 2 items from the stack, performs 3 minus 4, and puts the result of -1 on the stack. Okay, so, actually, I guess if you read this, this is the answer to the Leetcode problem. So this operand is not actually put onto the stack based on this explanation. This operand, let me go in here and give me some room. This operand plus and this operand minus is not even put onto the stack, right? Once you know that it's an operand, you know that your job is to look at the last 2, right? Go ahead and last 2 here, last 2 here, the last 2 numbers in the stack, and perform the operation. All right, at the end of it, you are left with a single value in the stack, which is this 4. And if we use their example, it would be, well, this is their example, actually. So it's 3 to 4. It's the operand over here and here. It seems like what's important for the operand, not for plus, but for minus, is the order of the operand. So if you put the 3 and the 4, you have to make sure that, it becomes a 3 minus 4 operation and not a 4 minus 3 operation, right? Okay, so the subtraction operator removes the top 2 items from the stack, performs 3 minus 4, and puts the result of -1 onto the stack. A common terminology that is added is that added items are pushed on the stack and removed items are popped, right? So we know this, right? So you push, push it. Let's say you're pushing onto the stack. Hopefully that looks like a push. And then when you're popping off the stack, right, to do this, I guess this right here, to do this operation, then that's going to be a pop. And how do I demonstrate a pop? I guess this thing's a pop, like if it was a balloon or popcorn is a pop, right? Or just a word pop. Maybe that could be a pop. So it's popped off the stack, right? So this is a push, and maybe a push is blue, and the pop is yellow. The advantage of reverse Polish notation is that it removes the need for order of operations and parentheses that are required by infix notation and can be evaluated linearly left to right. For example, the infix expression 3 plus 4 times 5 plus 6 becomes 3, 4 plus 5, 6 plus, and then the x at the end of it. Interesting. Okay. That's really cool. So that's an advantage for us, and it's something that's good for us to know because, if you look at this problem without reading the Wikipedia article, you might think that parentheses could mess up some of the code, right? Like if you had to evaluate parentheses in the middle of of an equation, you probably couldn't just put it on the stack, right? You'd have to search through the stack to find the parentheses, and you know, if the job was to convert an infix notation to a postfix, you might need to do this type of search and find, right? But we don't have to do that because in the problem, it assumes that it's already a valid arithmetic expression. Awesome. Okay, so what is what's the code that we're gonna need? Let's just think about it. So we have this example: tokens 2, 1 plus 3 multiplication. Okay, so from what we know, let's say we had a single stack and we put a 2. We put a 1. Okay, so let's say we had a solution function and it takes this list of tokens and we iterate through the tokens, right? So for t in tokens, if it's an operator, we're going to do something else. It's a number, right? And if it's a number, we're going to push onto stack. And then if it's an operator, we're going to take 2, or let's use the correct term, pop 2, and with the correct ordering, we're going to do that operator with that 1 and that 2, right? And then I guess we're just going to put that right back on the stack, and then push to stack. And then at the end of it, we want to return this item that's in the stack, right? And it's going to be the only item in the stack. So let's walk through the example. So in the example, it's a 1 and 2, right? Not an operator. And then we actually have an operator. So I'm going to go ahead and make, which color did I use before? Make these gold and make this red. We see an operator. So we pop, right? So we pop this, and it's going to be the 2 plus 1, which equals 3. And now the stack, I'm going to be putting it back on. That 3 is now, go ahead and X this out, pretend that doesn't exist. And now we have a 3. All right, go ahead and X that out. And then we have the next item is a 3, right? Push that onto the stack, and then we get a multiply, right? Make that red. And what's going to happen here? Same thing. We're going to pop 2 off the stack, this 3 and this 3. Do a little multiply. That's going to be a 9. And then on top of the stack will be a 9. Sorry, I should have shown the whole thing here, but this is the example. So yeah, it's the same with the other ones. I guess the thing that's different we have to take care of is the ordering, which we pop, and the division, right? So let's look through example 2 just to get a feel of it, right? Let's say we have a stack, right? We put the 4 on, we put the 13 on, we put the 3 on, or sorry, the 5. We see a division. Division's going to take this 2 and do 13 division. And, hopefully that's going to be 6.5, but then round it down to 6. We're going to put the 6 on, and what's going to disappear is, I use gray to make it disappear, this one, and this one, right? And then we have a plus, right? Plus operator, and what that's going to do is going to pop these 2 off the stack, this 4 plus this 6, this equals a 10, this goes onto the stack, and we are going to lose this plus, this 6, and this 4. Okay, so I think that's enough drawing examples. We pretty much, this was the hardest part, actually, getting a sense of using the stack there's a couple things that we're gonna make sure that we have to handle, or we're gonna fail. Number one is division goes towards 0. We have to remember to do that. And number two is we have to consider the ordering. So when we turn this into infix, we have to consider that when we pop, that becomes the second operand. We pop again, that becomes the first operand, right? All right, so let's just pull up our little editor here that we got and implement some of what we have. So we have to make the stack, and we're going to implement this with a list. We're going to pop off this list, right? And we're going to iterate through the tokens. So for t in tokens, we need to check if it's if operator, we're going to do something, and if number, or else, and that's going to mean it's going to be a number, is number. So if is operator, else is number, we're going to do something else. If it's a number, we're just going to do a push. And if it's an operator, we're going to pop twice, right? With the first pop is the second operand. And the second pop is the first operand, right? Which means in the equation, if we're going to do it in fixed style, it's going to be the first one. And division goes towards 0 is something we have to consider. So how do we check if it's an operator? Well, we know that the operator can only be these 4, so we can check if it's in this list that we have here. So it's if it's this, if it's that, if it's this, or if it's this, right? Plus, minus, multiply, and divide. So if it's an operator, we pop twice. So I'm going to go ahead and just call this the second operand. Will be the stack.pop. And then the first operand will be the stack.pop here, right? And then, well, what are the operators? So if the t is a plus, then we're going to do addition, right? So if t is a plus, then the result is the first operand. Okay, I don't want to write all those out. So I'm going to say op1 and op2. So op1 plus op2, and then we want to push that onto the stack. So stack push result else strange, got some weird tabbing behavior here. Okay, there we go. Else if t is minus, then we want to do stack push, and that's going to be op1 minus op2. Else if t is multiply, then we want to do op1 multiply op2. I'll spell that correctly. And then else here it would be divide. So what we want to do is divide it. So op1 divided by op2. Now let's think about this. This is going to be a decimal float divide. If we do this, this is going to get rid of the remainder, but it won't actually move it towards 0, because in this version 7.5 becomes 7, but negative 7.5 becomes negative 7, right? So we need something that turns it into an int, but towards 0. And curiously, the thing that does this is casting this to an int. So if you cast this to an int, it's going to move that towards 0. I guess that makes sense. Gets rid of these decimals, and that's what it's going to do. I just realized we probably need to cast these to ints. We haven't done that yet, so let's do that here. We will probably not want to add two strings together. Probably want them to be some type of integer value so we can do an operation on it. So here's the plus, here's the minus, here's the multiply, and divide. I'm going to go ahead and stack.push. Division of this, cast to an int. We handle this comment. And I guess if people want to be consistent, they can go ahead and do that as well. Okay, so here, oops, that was a comment. So here, we're going to push, right? So stack.push, we're going to push t, which is the number. I guess what we could have done also is we could have pushed the int here, and then that requires us not to do this, because this stack will be a stack of ints, and that can give us some better confidence that down the line we're not going to forget some type of int conversion. Okay, and we return the stack, and there should only be one item in the stack if they've given us a valid reverse Polish notation. So this code is exactly what we wrote here in the simplified pseudocode version. And it should match what we drew very messily over here. But hopefully we're doing right by this guy, where numbers are being pushed, this 3 and this 4. When there's an operand and it's being pushed, we pop the two numbers. First operand, so the first one that's popped is going to be the second operand, that's op2. The first one, when we pop again, that's going to be op1, and that's how we're going to perform this operation. Let's run this and see if it works. Ooh, invalid syntax. So if t is in, so t, I don't think there should be an is. If t in, so maybe Python is not as close to English. List object has no attribute push. So push is push is a terminology that they're using for the stack, and that is classic terminology when you're using a stack. Because we're using a Python list, Python's list doesn't use push. It uses append. So we're going to append onto this list. Going to have to change it everywhere. So if you're thinking about stacks, the way you're going to communicate about it is push. But the syntax in Python will be append for a list. Okay, so it works for these 3 cases. There's probably some cases I should have checked. I guess if the tokens were, tokens was an empty list, could have done something more efficient here. All right, so the runtime, what is the runtime? Well, we have stack here. For every one of the items, we have to push it onto the stack. And then for every one of the items, we have to pop it off the stack and do a calculation, right? So it's going to be O of n for the push, O of n for the pop. And I guess for O of n divided by 2, there should be a constant time operation. So it's O of n. And yeah, and it looks good. So it's possible we could have got very creative, even though this is historically done with a stack. It's possible we could have been very, very creative and done this without a stack. But if you're going to do it with a stack, this seems like the way to do it. Anyway, this was an interesting one. I'll probably, after this one, do a deep dive on these calculators and see, um, the motivations behind this. It makes sense. You don't need an equal sign. This hat totally makes sense. Instead of, 3 plus 4 equals 3, 4 plus, the plus implies that you want to do a calculation. Pretty interesting. Anyway, thanks a lot for visiting. I will see you next time.